Alrighty, welcome back to 353. Slight technical issues, but we're back on track. So, let's start off. So, if you are interested in writing your own operating system, not exactly where this course is aimed at, but you can actually start reading this now. So, from the graduate MIT operating system course, there is this XV6 kernel for written specifically for RISC-V. You can run it in QEMU if you want. That would mean you're running it in a VM in your VM, but it's a re-implementation of Unix for RISC-V in C. And you can actually start reading it now. So here is their init process. So remember, init is supposed to be responsible for spawning, either directly or indirectly, every single program and also acting as the orphanage. So we can actually kind of read this now. So here, their init process is just responsible for launching sh, which is the shell. So first it starts up, it does open console, and well, the console is basically their terminal. If it's successful, it will return file descriptor 0. So that would be standard in, and then they do a dupe, which we'll get into today. But that basically just returns a new file descriptor that points at the same thing as file descriptor 0. So file descriptor 1 and 2 also point to the terminal. Then it has this handy dandy for semicolon, semicolon, which is just a fancy way of saying while true. So while true, it says init starting sh. Then it forks. Everyone knows what fork is now. Checks if PID is less than 0, meaning there's an error, in which case it exits init, which exits the entire operating system. Otherwise, if PID is equal to 0, then it execs, so it starts running as the child, the sh program or the shell. And if it's successful, then that new process starts running the shell instead. If it is unsuccessful, exec returns an error. They don't check because it has to return an error to reach this print line. And they just, again, just say exec sh failed and then exit. After that, it's another infinite loop in the other infinite loop that says this call to wait happens if the shell or if another process exits. So it's just an infinite loop that waits. So this is it acting as the orphanage. So it just calls wait over and over and over again. And it has a little check here that if the process ID it gets back is the shell that it launched, all it does, it breaks, which causes it to just relaunch another shell. Otherwise, it checks for an error. And otherwise, it was a parentless process, so it adopted an orphan. It cleaned it up so it will do nothing. And that is the entirety of the init process for a very, very simple operating system. So we can see that it indeed has two jobs. And this does the two jobs, right? It launches the shell, which the user types in to launch other programs. And it also is the orphanage because it just calls wait over and over and over again. So any questions about that? We can now read operating system code. Neat. All right, so we'll get into a bit of theory. Most of today is going to be a lot of programming classes or programming practice because, well, managing children and forking and killing them is hard work. So we will get some more practice with that today. But before, there's something called uniprogramming for old batch processing operating systems. So probably much, 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 much older than you, but back in the olden days with DOS and whatever the hell came before that, you could only run one process at a single time, which is a bit limiting. So that was called uniprogramming. So if you have two processors, they're not run in parallel and they're not run concurrently no matter what. We can only run one process at a time, which kind of sucks. Every operating system since, I don't know, the 80s has been multi-programming, so we have multiple processes all going on. Two processes can run in parallel or concurrently. Again, we don't know exactly what these words mean yet, but we will get into them in about week 5. So only thing we need to know is that modern operating systems now try to run everything in parallel and concurrently, so it could be juggling thousands of different processes. You can open your activity monitor or open your task manager or whatever and see how many processes your operating system is actually juggling between. It is going to be at minimum probably hundreds. So another talk about that, juggling different processes. There's something in an operating system called a scheduler, and that decides when to switch between running different processes. So to create a process, the operating system has to at least load it into memory, right? And when it's waiting or in that ready state, the scheduler, which we will argue about in a bit, decides when to transition it from ready to running. But first, we're going to focus on the mechanics of actually switching which process to run. So where it fits in, there's this core scheduling loop that runs in kernel mode because it has to it has to have control over all the processes, and it changes which process runs. So it basically has 4 steps that all go in an infinite loop. So our 4 steps are, it will pause the currently running process that is running on a CPU, so it will stop it from running. It will save its state, so you can restore it later, aka the value of its registers, so they're consistent between when it gets switched out and in. The scheduler will figure out the next process to run, and then we will load that process's state, so we'll restore that process's state, and then let run directly on the CPU. So it would restore, at minimum, all the registers from whenever that program was last paused, and let it get control over the CPU again so it can run. So there's 2 different ways operating systems can actually maintain control. We can let processes kind of manage themselves and figure out when they should run, or have the operating system pause and have the operating system or the kernel maintain control. So there's something called cooperative multitasking. That means the process has to explicitly use a system call to tell the operating system that, hey, if there's something else to run, you can run it. I will give up the CPU so that I will be nice, and something else can run. If you don't do that, then you just run until you're done, and you kind of hog the CPU, which may not or may be good, depending, again, on the scenario. Most general purpose operating systems have something called true multitasking, where the operating system, specifically the kernel, retains control and will pause the processes without them having to opt into it. So to do this for true multitasking, the operating system can give a process a set time slice and be like, hey, you can execute for 100 milliseconds, and then you're done, and we have to go to the back of the line. Or it can maintain control by just waking up periodically using interrupts, and then use that to do the scheduling information, kick out a process if it thinks that, hey, it should be kicked out. So that swapping of processes, specifically the terminology for that is something called context switching. So at minimum, we have to save all the current registers because, well, that's what our program actually needs to run. So we have to save all the values using the same CPUs we're trying to save. Might sound a bit tricky. It's actually not that tricky. You can just save the value of all the registers on the stack, and then knowing how many values you save, you can recalculate the old stack value if you really want. You can see that in the teaching operating system kernel. For now, we don't care. Just know that context switching will save the state of all the registers somewhere. So there could be some hardware support for saving state because, well, if you have 200 registers, putting 200 values on a stack probably is not the greatest. So some CPUs have special instructions for saving the whole state somewhere, but maybe I don't want to save everything. So context switching is something called pure overhead. The goal of operating systems is to run our processes, right? We don't care about how long the operating system takes to actually do a bunch of busy work. We only care as users that our programs run as fast as possible and no other time is wasted. So overhead is just time wasted not running your program, not doing anything useful. So if context switching or just swapping out a process took 50% of my overall time, then your operating system is going to run pretty much twice as slow as any other operating system on the planet to run your program, and you will probably never ever use it. So we want it to be as fast as possible. It should be somewhere between, most operating systems, it's under 1% of the total time is spent context switching. So it's more or less negligible. So you can do some smart things to make sure you only save what you need. So you can have like a combination of hardware and software to save as little as possible. One example would be like there are certain registers for floating point operations. And if you're smart enough, if the kernel's smart enough to figure out that, hey, your process doesn't use any floating point operations, then it doesn't have to save any of the floating point registers to restore them if you're not going to use them anyways. So the goal is to just be as lazy as possible, only save the minimum amount that we actually need so that things still work. All right, now we get into the new API time. So there's this new API called a pipe. We saw how the shell uses it. So remember the bar between two processes. Technically, it's called a pipe, and we can actually use it in our programs. It has an associated system call with us. So the pipe system call, it takes as an argument an array of 2 ints. If it's successful, it will return 0 on success, -1 on failure, like all of the wrappers for system calls do. And if it's -1, it will set error no. And what pipe does is it will form a one-way communication channel using 2 file descriptors. So this array of 2 ints, it will assign 2 integers, so one at index 0, one at index 1. And the file descriptor set at index 1 is going to be the read end of the pipe. So I am allowed to do read system calls using that file descriptor to get information out of the pipe. You can think of the pipe as just like a kernel-managed buffer or just, I don't know, a dumping grounds for information in the kernel that you can send bytes to and read bytes from. So the file descriptor at index 1 is the right end of the pipe, so I can use the write system call to send bytes into the pipe and use the read system call to get bytes out of the pipe. And I can actually use that if I'm clever enough to do communication between processes. So again, think of it as a kernel-managed buffer. It's just some memory in the kernel that is actually accepting some information when you write to it, and when you read from it, it will read that information. So we'll see how this is used and how we kind of implement that bar operator. So here's an aside. Someone mentioned the fork bomb before. So as an aside, you can use the ampersand in your shell. If you use ampersand at the end of your command, your shell starts that process and immediately returns. So if I do sleep1 and ampersand, I'll immediately tell that, hey, I can actually write in my terminal again. That's because essentially it will do a fork, and then it will not wait for it. It will just fork it and then just let it fly. And then it will just complete in the background. It doesn't explicitly wait for it in order for you to actually regain control of your terminal. So you'll see some output of the PID to let you know when it's finished. So it will clean it up. But that bar character, again creates a pipe between 2 processes. So someone said fork bomb before. So in Bash, you could do this sneaky command to actually perform a fork bomb. And it looks a bit stupid, but how you read this, it's intentionally supposed to be kind of obtuse. So what this actually does is everyone knows kind of how to define a function in C, right? You give it like a name in the brackets. In Bash, you don't say what the return type is because it's Bash. So turns out you can actually define a function called colon. So this is what the first line does. It defines a function called colon that takes no arguments. And inside, it's like C, the curly brackets are the body of the function. So the body of this function calls colon, which is itself, and then does a pipe to another colon, which again is itself. So this will call itself. And the ampersand just forks it off and then just continues executing again. So this semicolon ends, so that defines a function called colon that will call colon piped with itself and launch it off in the background. And then this colon sets off the fork bomb. So that calls the function we just defined. So that will do the same thing as doing while true fork, just in a sneaky way. So if anyone you know is running macOS or Linux, you can say, hey, look at this cool command that will give you a bunch of Bitcoin or something like that, or Ethereum or whatever is cool, and tell them to run that, and then they fork bomb themselves. So do not run this command on the school machines or anything like that. You can just annoy your friends, but you should help them fix it after you have fork bombed them. So that's just an aside. Yeah, of a sneaky way to fork bomb. So let's see an example. So what we're going to do is, let's go here. So close that. So we are just going to write a little program to show how to use a pipe. So we're going to communicate across two processes using a pipe in this case. So what we are going to do is, well, first let's see all the stuff we have written. So I have this little check helper that takes as an argument a return value and then a message. And again, this is just so I don't have to do any explicit error checking over and over again. All the C wrappers return -1 if it's a failure. So if it doesn't return -1, it means it's OK. Other than that, there's an error. I'm going to save error no, print out the error, and then exit the process. So first thing I'm going to do is I am going to, well, first declare an integer array of 2 file descriptors. I'll creatively call them FDs. So this is an int array of 2 ints. And then I'm going to call pipe. So pipe, I will give it the file descriptors and then a message if it fails. So by convention, whenever I launch my program, file descriptor 0, let's say FD0, that's standard in, which I can read from. Then I have FD1, which is standard out that I can write to. Then I have FD2, which is standard error, which I can also write to. So if I call pipe, if it's successful, I get 2 new file descriptors, right? I'll likely get file descriptor 3 and file descriptor 4. And this will get, 3 will get assigned to FD's 0, and this will be the read end of the pipe. And FD's 4 will get, file descriptor 4 will get assigned to FD's 1, which is the write end of the pipe. And one way to remember which index is which is they kind of line up with the standard file descriptors. So standard in is 0, and that's one you can read to. Same with index 0 for what's returned from pipe. So I can only read from that file descriptor. And then standard out, which is 1, I can write to it. And same with this index. I can write to index 1. OK, so this by itself is kind of useless. I just set up a pipe. I want to communicate between 2 processes. So if I want to communicate between 2 processes, well, I should probably make another process, right? So I could do int PID equals fork. So after the fork, what happens? So let's, again, assume we have process 100 running. So if process 100 calls fork, in this case, what happens? Uh-oh. Yeah. Yeah, so we'll create 2 processes, right? So it will probably create process 101, and it's going to look like 2 return from fork. And in the case of process 100, fork returns 101. And in process 101, fork returns what? Yeah, 0, right? It is the child. So it's a bit different than before. So I have a pipe before the fork. So because I have a pipe before the fork, the 2 children are going to look exactly the same at the time of the fork. So both process 101 and 102 will also have file descriptor 3 and 4 open, and they'll both have the array, and they'll be set to that. And basically, a file descriptor points to a file. So they'll both be pointing to the same thing. So in process 100, it has file descriptor 3 that points to the right end of the pipe, and same with process 101, it has file descriptor 3 that points to the same read end of the pipe. So if I want to communicate between 2 processes, what I could do is something like, I don't know, let's say if I am the parent, I can do something like maybe I want to just write some bytes to the child. So I'll declare something called a string. Let's say I just write, hello, my child. Something that's not weird. And then I could do write. So if I want to send information from my child to communicate between the processes, I can write to the right end of the pipe. So I can write, in this case, to fds1. And what I will write to it is the string. And I'll use string length of the string just so I only write the contents of the string. So that should write the contents of the string to my child, right? Everyone okay with that so far? And we'll kind of break it down. Yeah?
Why are you not writing to FDS3?
So why am I not writing to FDS3? Like if I just write, wait, FDS3? Like that?
Did you say something about like FDS3 equals like FDS0?
So the file descriptors, they're always sequential in your process. So the pipe system call is going to create 2 new file descriptors in your process. And because by convention we have file descriptor 1 or 0, 1, and 2 open, the next available numbers sequentially are 3 and 4, right? So that means pipe, if it's successful, it gives me 2 new file descriptors, which will be number 3 and 4, like the actual value of the file descriptor. And then it will assign it to this array of FDs. So it will assign the value 3 to FDs at index 0. So it just writes it to that array. But if I look at, like if I actually did something like, if I printf FDs 2 or FDs 0, let's just exit just to make sure it's easy. Oops, Mason compile. So if I do something like that, this is called, what the hell is it called, pipes. So if I do something like that, the value is 3. But I should just use whatever value I got returned from me. Because I'm not guaranteed it would be 3. I just know it's going to be 3 just based off how things are usually set up. OK, so I go back here. I should use FDs 1. All right, everyone OK with that so far? So that is what the parent is going to do. In the child, I'm going to, which is a different process, I want to read the bytes that my parent has given to me. So I can just declare my own little buffer here of magical size. And then I can just do a, well, size g bytes read equals, I can do my read system call. So I can read from FDs 0, so that's the read end of the pipe. And I can read it into the buffer with size of buffer. And then, again, I should probably check for errors. So I can check the bytes read. And then my error message could be read. And then similarly for the write, maybe I want to go ahead and check for errors here. So size t, bytes, bytes underscore written. And then check bytes written, right. All right, so there's error checking just to make sure. So now if I do this and I run it, what should I see? Well, let's try it. Trick question. Nothing. Because I just read that information. I didn't do anything with it, right? I didn't print it. I didn't do anything with it. So both my parent and my child just kind of exit. So if I want to go ahead and read what the child just, or print what the child just read, well, I didn't screw with my other file descriptors. So I could print f, let's see, what I read from the child. And the format descriptor I could use is I could do something like this. Has anyone seen that before? as a format specifier. Looks kind of weird, right? So it's a string format specifier with a width, so it will only print a certain number of characters given by the first argument. So because I'm not guaranteed what I read was a C string, so I could only actually use bytes read from it and do bytes read from the buffer, and it will only print off that number of characters. So we still have a warning. Oh, because it wants it to be an int. OK, well, I'll make it an int just to make you happy, because I know it's within limits. So if I do that and run it now, I can actually see I'm actually communicating between two processes. So I read, hello, my child. So that came from my parent. So my parent wrote to it. And because I was using a pipe and I shared it between two processes by only forking after the pipe, so both processes had all the same file descriptors open, I could effectively use that to do IPC or interprocess communication. So the parent wrote, hello, my child, to the pipe, and then the child read it. Yeah?
Does the read function have some kind of like synchronization to make sure that you actually wrote new information to the buffer?
So
Or do you get into a situation where we like make the parent sleep and it's just going to print out garbage?
So question one is there any synchronization with read that will ensure things happen? So read is a blocking system call. So yeah, we don't know which order these are going to go in. So if the child hits read first, it's going to sit there and block at read until the parent writes to it and there's actual information. So that is OK. Doesn't matter what order they're going to run in. I'm always going to read hello, my child. But good question. Was that everyone's question? Yeah.
What happens if the parent and child both write?
What happens if the parent and child both write?
Have a synchronization function, because the parent and the child can both also try to write at the same time.
Yeah, so a pipe is a one-way communication channel. So if both the parent and the child write to it, then who should read from it? Who's communicating with who? So we'll see a more complicated example after the break where we need to use two pipes, but for now, we're just going one way. Yeah?
Can there be a case when there's nothing to read if the parent hasn't communicated anything yet?
Yeah, is there a case where, what happens if the parent is just kind of a jerk, right? What about if the parent's just kind of a jerk? And let's see, the parent just like, hey, child, they're not on speaking terms, right? So we just don't write anything. Let's just comment out everything. So they're not on speaking terms. Well, what might happen? So create a pipe, OK. Fork, they're both the exact same. They both have all the file descriptors open. And then the parent just exits immediately. And then the child hits read. So our question might be, well, does it read nothing? Does it get stuck here? What happens with it? So we should be able to investigate this just by running. So, whoops. Ugh. Typing standing up, looking at a screen with lag is hard. All right, so if I run it, it looks like nothing happens, right? But how can I check if I created an orphan or not? Because that could be a possibility, right? If my child got stuck in this read, I could have created an orphan because it should have printed something here, right? So it kind of looks like it's still maybe chilling around, it's still running. How would I check if I created an orphan? Sorry? Yeah, PS, or if I know the name, I can try that PID of. So PID of, it was called pipes. So if I do PID of pipes, oh, look at that. I have a child process chilling there, orphaned. Turns out that what happened is the child calls read, but the parent kind of ignored it, right? So the parent kind of ignored it. This read blocks. It's waiting for information. And there's a subtle thing. Remember, read returns 0 when it's end of file, right, or no other input is possible. In this case, this will be fun in lab 2, so this will be one of your first debugging things in lab 2, is in this case, read will not return 0 because it's still possible for information to go into the pipe. You might be wondering about that. So let's try and draw a little diagram here. So what we have, if you can excuse my horrible, horrible penmanship, is, let's say we have process 100. So we have process 100. I'm only going to care about its file descriptors used for the pipe. So one way to illustrate the pipe is this handy dandy pipe. Look at that. Doesn't that look like a great pipe? So the way I represent a pipe is that FD's 1 is the right end of the pipe. So if I write any information, it goes into the pipe. So if I write, in this case, I'm writing the string hello and a whole bunch of other stuff, right? So that information, in the case where it actually worked and the parent wrote something to it, the parent wrote from there, and then the child, whenever it read, it got that information out of the pipe using FD's 0, right? So when it called read, it took that information, got it out of the pipe, and then that process read it. And how this worked and how I was able to do it across 2 processes is because, well, I created the pipe before I forked, so both processes actually were complete clones of each other after the pipe was created. So process 100, its file descriptor 3 in this case, whoops, or its FD's 1 pointed here. And same with process 101. It had a variable called FD's 1, and it pointed to the exact same thing. And then they both also had a variable called FD's 0. So FD's 0 point to the read end of the pipe. Right? And how it worked is, well, my parent process, in this case parent or process 100, it wrote data into that pipe, right? So it used this file descriptor to kind of add data into that pipe. And then process 101 used this file descriptor to get data out of that pipe. So everyone okay with this? So turns out what happened and what will be the first confusing thing is the orphan we created, it was blocked at that read system call. So read will block until someone writes to that pipe, or it's not possible to get any more data into that pipe. So in this case, if process 100 dies, then all of its resources get freed along with its file descriptors. So now it looks like this. So now what the operating system asks is like, hey, for this pipe, is it possible that a process can write to it? And it knows that by if a process has an open file descriptor to the right end of the pipe, it assumes it's possible for that process to actually write to that pipe. So is it possible that process 101 writes to that pipe? Yeah, I mean, currently it's blocked reading on it. So you might argue that, hey, well, it can't really write to its own pipe because it's waiting on it. But then you have to remember that signals are a thing. So you could send it a special signal such that the signal handler actually did the right end of the pipe, or like wrote information to the right end of the pipe. So the kernel has to be conservative and assume that, hey, data could go into that pipe. So I can't actually assume that it is closed. I can't send that end of file notification because it's possible that some other process or a process writes data to that pipe. So if I go back here, all right, so there's my orphan process. Again, only in this course. How do I murder my orphan? Yeah. Yeah, I can kill -9, or I could just kill it. Doesn't matter. So it should nicely close. Let's just kill violently my orphan, just to make, whoops, wrong process ID. So I can kill it. It's dead. It's gone. We've cleaned it up. No more orphan, no problem. So first word of advice is going to be to close file descriptors in your process as soon as you don't need them. So in the child process, does the child process ever use the right end of the pipe? The answer to that is no. So even if my parent ignores me, if I'm following my own advice, if I'm following my own advice, after the fork, I should close a file descriptor if I don't use it. So the child does not use the right end of the pipe. So which file descriptor should it close? Check. Help. FD's 1, right? Oops, close FD's 1. So that's the right end of the pipe, so it should close FD's 1. And then we'll check for errors and all that stuff. So this is going to be one important thing. So let's compile again. Oops. So if we compile again, we should see that whenever the parent dies in this case and doesn't write anything to the child, whenever the parent dies, its file descriptors all get free. And because we close the right end of the pipe in the child, when the parent dies, no single process on my machine can access the right end of that pipe. So read should return 0, indicating end of character. And in this case, I'll just get read with 0 characters written. So if everything works properly, and I run this, I should see, again, read with nothing. So, and if I look, I didn't create an orphan. I didn't do anything like that. I'm all good. So questions about that? And again, this will also work if I uncomment this out. If I uncomment this out and run this, run it again, then the child actually reads data because if the parent is still alive, it has the right end of the pipe open. So read wouldn't return 0 if the parent's still alive because the parent has the right end of the pipe open. So it's going to block there until either the parent closes the right end of the pipe or it writes information into it. So in this case, it will block and it will always read, hello, my child. Yeah?
Will the kernel still close the pipe if, like, say, only something can write to it, but nothing can read from it?
Sorry, if only something can write to it?
In our example, we close the writing side to the pipe.
Yeah.
And what if we only close the reading side?
So if I have no readers anymore, like no process has the read, yeah, so if no process has the read end of the pipe open, then anything you write to it goes nowhere. And you actually get an error if you write to it. Say, I believe the error is like epipe or something. That's like, hey, you're writing data that essentially goes nowhere. Is that a question? Yeah?
In this example, is the right side the read end?
So the, so yeah, I write that writes go in here, and the right end is FD's 1, and I don't know, it just I think it illustrates better like this, and the read data comes out of it. Yeah?
Just wondering that, say, if in this code we change it such that the parent also closes the read side from the pipe, and would there be a case, or would there be a chance where the child, like the child runs first, but the parent already closed the read, or I don't know which order it was, like parent tried to write to the pipe that the child already closed, the parent already closed the reading side, but nothing else.
Yeah, so I have a few things. So if you didn't catch that, I didn't really follow my own advice here, and it might be confusing what happened. So does the parent use the read end of the pipe? No, right? So if you follow my advice, it should actually close the read end of the pipe. So I can do ye old copy paste. and then change this from a 1 to a 0. And then I can have my parent close the read end of the pipe. And the question might be, well, doesn't that cause any issues? So like the parent closes the read end of the pipe, does that cause any issues in the child? And the answer to that is, let's compile and run it. It just, no, still works, still fine. And the reason for that is, well, the parent, they're independent after the fork, right? So if the parent closes the read end of the pipe, it doesn't affect the child. So the child still has the read end of the pipe open. The parent never used the read end of the pipe. It just so happened that it wasn't terribly important. So if I ignored it, it didn't cause any issues. But if I forgot to close the right end of the pipe, that was more important, and that actually did cause me issues. Yeah?
So the parent is only closing its own read end of the pipe or its own write end of the pipe.
Yeah. So after the fork, the two processes are independent. If I did something like, let's say I accidentally move it here. So what will that do? Yeah.
Both processes will not have a read end, like they won't walk off.
Yeah, so if I do it before the pipe, right, I create a pipe, I have a read end and a write end. And then right now, this is before the fork, I assume only one process is running main. So that one process, let's say process 100, closes the read end of the pipe, and then I fork, so I create a new process. Well, they're exact clones at the time of the fork. That new process doesn't have the read end of the pipe open because, well, I didn't have it open before the call to fork. I closed it. So this might be another error that happens to you, in which case if I run this, I'm probably going to get some weird errors where read says bad file descriptor. So one option is, well, the child tries to read from the read end of the pipe, but I already closed the file descriptor here above before I forked. So I tried to read from an invalid file descriptor. Good thing I checked for errors, though. Whew. Yeah?
So we have independent like pointers to the read and write ends of the pipe for the parent and child.
Yep.
Can we not have the parent and child both write at the same time then?
Yeah, so if you write it weirdly, the parent and child could both write to the right end of the pipe. But you probably don't want that, right? Because, right, what about if I did, let's see, what about if I did something silly? So what about if you were like, hey, I want to use a pipe, but I don't need to use it for processes. What about if I did something really strange? What about if I just got rid of the fork? I was like, whatever. What about if I did something like this? Would this work? No? It won't work? Well, let's build it and try it. Why does that work? Yeah.
It writes to the right end and it reads to the read end. So.
Yeah, well, it's all within the same process. This is just a stupid way to communicate with yourself, right? So it opens a pipe. It doesn't fork. It writes hello, my child to the kernel. The kernel has its own buffer, and then it reads information it just wrote. So if you end up doing something like this, so remember when we straced node and it was reading and writing a star? It was essentially doing stupid crap like this. But if we were smart, right, if we were smart, we just do that, and the string's hello world, we don't have to communicate with ourselves. It's right there, that's the string, right? That's completely useless. Yeah?
If both the parent and the child read from the same pipe, do they read the same message or do they like, read the message sequentially?
Oh, that's a good question. So, which is a bit more complicated. So this is what we had before, right? So the question is, well, if the parent also tried to read, what would it read? I'll flip it a little bit and just say, assume we have 2 children that try and read it instead of just the parent also tries to read it. So I could do that if I just did a fork here, right? If I did a fork here, then I create a new process that's a clone of this child. The original child's going to be the only thing that reaches it. So they're going to be exact clones of each other. They're both going to have the read end of the pipe open. And one question might be like, hey, if two processes are trying to call read to the same read end of the pipe, do they read the same data, or is it sequential, or what? So I know the answer to this. The answer is that it's sequential, but in case you don't trust me, in this case, right, I'll have 2 processes calling read, trying to read the information that the original parent wrote. And in this case, if I print their file descriptors, I don't know which one is going to read it. All I know is that one of the 2 processes is going to read the whole message, and the other process is going to read nothing. It's going to read 0. So it's going to be sequential. So the kernel guarantees that whatever bytes you write to the pipe will only come out once. So if I run this, I can see one of them ran hello my child, and the other one was empty. All right, any questions? All right, so let's take our 10-minute break, and then we will have a more fun example. Whoops, break. Alrighty, let's do something way more complicated. So if one pipe is fun, 2 pipes is more fun. So we're going to do something much more complicated where we send and receive data from a process. Ooh. So our goals, we're going to create a new process that launches the command line argument that we type. Then we are going to send the string testing with a new line to that process, and then receive any data it writes to standard input. So some other APIs we need, and spoiler alert, this is more or less lab 2, so pay attention. So we saw execve before to run a different program. It was kind of a pain in the butt because we had to know exactly like the path of the executable, where it was on our file system. So there's a more convenient wrapper for the execve system call called execlp, and that will save us from writing out the whole path. So it just needs the name of the file, and then it also doesn't make us do an array of strings. We can just pass a whole bunch of C strings to the function directly. It just has to end with a null when we're done. Does the same thing, it's just a more convenient wrapper for us. Again, like the execve, it does not return on success, returns -1 on failure and sets error no. And again, it just lets us skip string arrays, and it searches for executable using a path environment variable, which is basically like a global variable for all executables. So you don't have to know how it works. Basically a global variable that tells you all of the folders on your system where there's executables, and it will try and find it in one of those folders or directories. All right, so our final APIs that we saw at the very beginning, we'll explain them now, are dupe1 and dupe2. So both of these return a new file descriptor on success, -1 on failure, and it sets error no. So it copies the file descriptor such that old file descriptor and new file descriptor point to the same thing. For dupe, it returns the lowest file descriptor. So for dupe, the file descriptor argument, again, think of file descriptors as pointers to something that you can read and write bytes to. So old file descriptor is just an index to some pointer that points to some resource. So it will return you a new file descriptor or a new index that also points to that same resource for dupe. For dupe2, you give it 2 arguments, old FD and new FD, and it will not modify what old FD points to, and it will make this number that you can specify point to whatever old FD points to. And if this second argument, new FD, is already open pointing to some valid resource, it will automatically close it for us as well. So we can essentially just make FD refer to a certain file descriptor if we want to, which will be useful because we want to communicate between different processes. So rest of it is just a coding example. So here is, we're going to need pipes. And again, we want to communicate across processes. So essentially what we want to do is create some process 100 that has some information, and we want it to essentially create process 101. This process should actually, start running a different program. So it should run, it should exec something. Let's assume we want to run, the process uname. So uname just outputs to standard error, or to standard out the name of the process. So maybe we just want to exec uname. And as part of that, we also want, whenever this process writes out information to standard out, we want to capture it. And we also want to write information to this process, in this case, the string testing with a new line. So if we want to communicate across processes, what do I need to use, or what did we just learn to use? Yeah, a pipe, right? So let's start tackling let's say we want to start tackling this pipe. So we want that whatever this process writes to its standard out, we want to capture it, right? That was our goal. We want to capture what it writes to standard out. So we need a pipe for that. So does this look okay for a plan for now? And we'll slowly go over it. Let's do the exec first. So everyone okay before I switch to the code? All right. So again, I'm going to split it off a little bit just to make it a bit more readable. So I'm going to create a few little helper functions. So I'll have check error, and maybe I just call it check, whatever. So I'll have my check function that again does the same error checking for system calls. And then I will have a function called parent that's only executed by the parent, because of course I'm going to fork. And then also I'm going to have a function called child that only executes in the child. In this case, I already put that exec VE there, and it's going to run some program that I give as a C string. And we can see I had a placeholder for pipes. So a pipe is a one-way communication channel. So I set aside space for 2 pipes. So in main, I check that I have exactly 2 arguments. If I don't, I return an error. Other than that, I just initialize my array of just to all zeros, just as a precaution. So I declare 2 arrays in pipe FD and out pipe FD, initialize them to 0. And then I fork, and then I just call parent, which with pipe FD, out pipe FD, and in the parent, I give it the PID of the child. So fork, it'll give me the PID of my child. So I pass that to this parent function. And then else in the child, it gets that 2 pipes, and then the second command line argument I give it. So even with this, if I run my program now and say I run it, I called this subprocess. So say I run it with uname. So by default, if I just run uname by itself, it just tells me the operating system I'm running. So it prints Linux. If I run my program right now, whoops, uh-oh. All right, I probably have to re-upload the recording, cool. Where'd that crash? No, we're still recording, good. All right, so if I run this program right now and say I run build, it's called subprocess. If I do subprocess uname, what do I see? Yeah, Linux, right? So if I run this right now, I see Linux. Everyone okay with that? Everyone could explain that? So my child runs, I create a new process, it execlp's uname, so a new process is doing that, but because I forked at the beginning, right, all my standard file descriptors are pointing to the same thing, so my child has all the same standard file descriptors, all pointing to the terminal. I don't change them or do anything with them. So when it prints Linux, that process, it does write to file descriptor 1, and since I didn't play with it, it goes to the terminal, just like the original process. But this is actually coming from the child now and not me running it. So everyone okay with that? All right, so if I wanted to capture its output, what should I do? So I want to get the string Linux, not to my terminal, but within my parent process. Yeah? Make a pipe. All right, so let's make a pipe. Let's call it out pipe FD. So in here, again, I'm trying to do this green one. So this green one, I'll call this one out pipe FD. So we'll do this one first. So we'll go back here. So we'll do pipe out pipe FD, and then make sure that our pipe doesn't return an error. All right, now what? So I created a pipe. It's before the fork, so both my parent and my child have access to that pipe. So what do I do now? I need to write to the pipe. Well, I want this to write to the pipe, right?
Capture STD out.
Capture STD out. So could we maybe make use of one of these? Oh, yeah. So we can't change what that uname is going to do, right? It's going to write to file descriptor 1. But we can change what file descriptor 1 points to. So if we want to capture what it's writing to file descriptor 1, what should we do in relation to our pipes? Yeah. Dupe to what? Yeah, so in the child, right? The child is what I want to capture output from. So conveniently, it gets out pipe FD. So what I want to do is I'll check. I want to dupe 2, right? So you said dupe 2. And I want to dupe out pipe FD what index? 1, right? So again, remember, the right end, kind of the index corresponds with whatever standard out is, which is FD1. If you want to remember it that way, not quite equivalent, but a good way to remember it. So I want to dupe the right end of the pipe, and what do I want to point to the right end of the pipe? Yeah. STD out, which is just the magic number 1, right? Just the magic number 1, or if you didn't want to, it's like standard out file no if you just don't want to hard code a value, but spoiler alert, it's just the value 1. So again, like with doing exit success and stuff like that, you know, if you can, you'll kind of remember the standard numbers, but I could do something like that. So let's make sure there's no errors or anything like that. All right, so is that done? Is that sufficient? Yeah. Oh yeah, I could probably close the other end of the pipe. Which other end of the pipe? The read end. So I could check close the read end of the pipe, which is out pipe FD 0, right? Oops, close. So is that all I have to close? Yeah. Oh yeah, well I should probably read it in my parent, right? I want to read it in my parent, otherwise that information's going nowhere. So yeah, maybe I do that part. So if I want to read it in the parent, I'll save you some time. I'll just do the standard thing we've always been doing, a magical buffer of some magical size, which we'll get into later. And then I want to essentially just read the read end of the pipe, right? So st size bytes read equals read. The read end of the pipe is out pipe FD 0. Read it into the buffer. Size of buffer, because it's C. Of course, we got to do that. Then I'll check the bytes read is OK. And then I could, you know, printf. Same thing, whatever I read. So same format string as before. And let's do, sorry, I have to cast it to an int, bytes read, and then buffer. All right, is this good now? So do we think the parent should read Linux from the process it creates? Someone's laughing at us. That's not good. All right, well, I don't know. Let's try it. So if we run that, hey, we read it, right? The parent read it. So we're communicating across processes. Have I skipped any steps? Yeah. Yeah. Yeah, I do want to read the string to it. We'll get to that later for this. Yeah. yeah, after the program finishes running, it should probably close the pipes, right? So where should I put some close calls? After the printf. So after the printf, what you want me to close the read end? And on the child, close the write end. So that.
I think you should close after the exec.
So you want me to close after? Yeah.
But it doesn't return from execlp's value.
Yeah, so if execlp runs successfully, it never returns, so it starts running another program. So this line, unless there's an error running a different program, this line will never get executed. So is there a problem if I do that?
Yeah.
Yes?
I think you put it after the dupe, maybe.
After dupe? That? So, well, we can see. So if we put it before dupe, I mean, thankfully we program defensively, right? So if anything bad happens, we should get an error. So if we do this, dupe2 says bad file descriptor. So that makes sense because I just closed it and tried to dupe it. So probably a bad idea. So if I do this, will this cause it to break? Well, let's see. So if I run it, it still works. And the reason why this works and why this should actually be, I would argue, preferred is because it is generally exceptionally rude to exec another program and have other file descriptors open beside the standard file descriptors. So when you exec it, the only things that should be open here are file descriptors 0, 1, and 2, and it's considered very rude if any others are open. Although someone should teach that to the VS Code developers because they leave weird things open. So if we were to argue what happens from the starting of this program, again, main starts executing. Let's say it was process 100. It would have file descriptor 0, which points to standard in, whatever that happens to be. Oops, too many. Standard out, standard error. Because we assume something reasonable launched us. Then whenever we call this pipe, we're going to get two new file descriptors, likely file descriptor 3 and file descriptor 4. Again, you should just use the values in the actual array just in case you're wrong. But for most sensible things, these are the values you should get. So this would be pipe FD 0 or the read end. And this is out pipe FD 1, the write end. So now we have all these. Let's indent them a little bit, be a bit nicer. So after we fork, right, we're going to have two processes that look exactly the same. So we're going to have process 101 and 100. They're going to have all the same file descriptors all pointing to the same things because they are exact clones of each other. So in the child, only the child is going to execute the child thing. So in here, if we close pipe FD 0, that essentially gets rid of this, right? So this is the read end of the pipe. If we close that, it is now gone. File descriptor 3 is not valid. Everyone okay with that? All right, so that's what happens after the first close. Then after the dupe2, what dupe2 is going to do is make whatever this file descriptor point to, which is right now file descriptor 4, which points to the right end of the pipe, and it makes this file descriptor 1 point to the same thing if it's successful. So what that will essentially do, in this case, since 1 is already open, it will just replace the original standard out with the right end of the pipe. And then in order to properly clean stuff up, we should do that final close. So right before the dupe2, our file descriptors in the child process look like this. And then when we close pipe FD1, that gets rid of this. So now file descriptor 4 doesn't exist. And now file descriptor 1 still exists, but now it points to the right end of the pipe. And that's what we did through that dupe2 thing. So now we only have those 3 file descriptors open, and we're now nice. So anyone have any problems with that? That looks good to me. All right. What about the parent part? So the parent part, again, my word of advice is to close file descriptors as soon as you do not need them. So in the parent, if we go here, immediately, what should I close? What do I not use in the parent? Yeah. Yeah, I do not use the right end of the pipe in the parent, right? So I should immediately close that, which I can just, do ye old copy paste. Make sure I copy and paste the right one. So first thing I do, whoops, I copy and pasted too much. So first thing I do is close the right end. So if I close the right end of the pipe, I got rid of that, right? So now in my parent, can I close the read end of the pipe? So can I just do, just immediately do this? No, yeah. No, why?
Because you haven't read from it yet.
Yeah, because I'm just going to read from it. I'm still using it. So advice is to close them as soon as you are done with them. As soon as you are done with them. I'm not done with it yet. I need to read. So here, as soon as I'm done with it after the read call. So we'll just have it go, let's say, oh, we already have it there. So we already have it there where we closed, so we cleaned it up. So at this point, our process 100, we properly cleaned up everything we opened, and it still just looks like that. So any issues with that? Yeah?
Yeah, just that we could have closed it right after the command.
Yeah, I could have moved it up slightly, so I could move it right after the read like that. Up to you. Doesn't really matter too much in this case. But if you want to follow my advice to the T, yeah, just move it up there. All right, other thing I might have is maybe I put a check around here just in case. All right, so that's good for reading information to that process, right? All right, what about if I want to write information to that process? Do I need a new pipe, or can I just reuse this one and also just write to it? Yeah?
No, because it has to be one.
Yeah, it's one way, right? So let's, oh no, tablet. So let's assume this out pipe FD, I was like, screw this. I'm going to just use this pipe to communicate between 2 processes. So in actuality, I'm going to use it like this, right? So it's going to use it, I'm going to use it to, process 100 is going to write bytes to this process, and process 101 is going to try and write bytes to that process. Reason why this is a bad idea, and something that you should be able to explain is, okay, so let's assume I had it set up nicely, that I had a different pipe that wrote the string testing to this process. And let's say instead of uname, let's say instead this process was running cat. What happens? What information is the parent going to read back from the child if that process is cat and I send the string testing to it? Uh-oh. Yeah. Does it hang?
If you like just use cat without like switching on the new file.
So we're trying to send this to cat, the string testing with a new line. No one knows what cat will output in this case. So we send the string testing to its standard in, and we get its value from standard out. So if we send the string testing to it, remember cat, it just reads from standard in and writes to standard out. What should we get out of it? Yeah. Testing, right? Just the string testing back. That's what all cat does. So if we write the string testing to it, cat we send the string testing to it, so we write it to the pipe. It would read it from the pipe, and then it would write it to the out pipe, and then we would read it from that out pipe. So we send information to it and get information from it. If instead we decided to just say screw it, or maybe we can just say screw it later. All right, do we want to just say screw it now and only use one pipe and see bad things? Sure, all right. So let's say screw it. Let's just continue writing, assuming we only use one pipe. So in this case, if I'm only using one pipe and I want to send the string testing to it, well, in the parent, before I close the right end of the pipe, let's just declare a string called, what do we say? We say testing. And then we will do size t, bytes written. So we'll write to the right end of the pipe the string, and string length, string. Check that we don't have any errors. And then that's it, right? So we're just going to write to that pipe and then read from that pipe in the parent, right? So I'm hoping to get that information from the child. So in that case, oh, I deleted too much. So in that case, before execve happens, if we want to plan what goes on in process 101, file descriptor 0 should be actually pointing to the read end of pipe or out pipe FD. And file descriptor 1 should be still writing to the right end of pipe FD. So we already set up this. If we want to set up the other one, what do I do to make sure that file descriptor 0 is the right end of pipe FD? Yeah. Dupe 2, right? So same thing. Before I close the read end of the pipe, I want to dupe 2 this to the std in file no, or just 0, and we'll give the error message. Okay, so we do that. Now we have it set up that in the child process, its standard in is the read end of the pipe, its standard out is the right end of the pipe, which I, of course, misspelled both times. Lucky me. And then in the parent, I write to the right end of the pipe and then read from the read end of the pipe, right? All right, so everyone thinks this is hunky-dory, all good? One-way communication channels are for chumps. So if I do that and uname, should this work? Well, let's run it, and then we'll argue about it. What happened there? Why the hell do I see? I want to see Linux. What the hell? Yeah, it's just reading its own right? So what happened is, well, in this case, I didn't read everything from the buffer. But in this case, the parent executed first. It wrote into the pipe, and then immediately read from the pipe. So it got the information it read from the pipe. So I can't really tell which way is which, right? And if I wanted to read everything, maybe let's organize this so that it looks like this again. So maybe I do another read call. And in this case, I can just reassign So if I do it again and have 2 read calls, then I'll see testing in Linux because one came from the parent and one came from the child, right? I couldn't tell, but I don't know which one came from which. I'm reading my own input. So if I was meant to send the string testing to that process, I never actually sent it to that process, right? Because, well, I read it. It didn't read it. I read it. So even worse, so if I do something like, I don't know, run cat, what's going to happen if I run cat? So I'll give you a hint. My laptop is probably getting warm. Or maybe it's not. Let's see how efficient we are. Oh yeah, that's not good. So all my cores are creeping up. Let's see, can I filter? So it's running, it's doing something silly. And it's just running forever. Anyone guess what the hell is going on here? So, yeah. Waiting for stdin to close? Kind of, yeah.
Cat just writing in and reading from itself over and over again?
Yeah, cat is reading and writing to itself over and over and over again, and essentially an infinite loop this time. So I'll Control-C to kill it, but basically what's happening is if I use this as a one-way or a two-way communication channel, right, I don't know which end is which. So this process is writing the string testing to this pipe, and then trying to read twice from this pipe. And then cat, all it's doing is constantly reading from the pipe and then writing that whatever it read back to the pipe. So in this case, I wrote the string testing to it, and then I read it immediately in the parent process. So if I was to draw what this did, so this wrote the string testing to the pipe, then read it back to itself. And then the way it was set up, that process 101, well, that we set it up so that its standard in reads from the pipe, and standard out actually, its standard out writes to the pipe. So what it's going to do, in this case, since we got lucky, it would just try and read from the pipe, and right now it's empty, so it's just going to sit there and kind of block forever, right? So it's going to sit there and block forever because I read that information. My laptop didn't actually get warm for that reason. If instead I did something like, I don't know, let's say I never read from the pipe. So if instead I never read from the pipe and only wrote to it, then I get into the condition where my laptop gets a bit warm. So if I do this and run it, did I write the string? Oh, because I nicely closed all my file descriptors and things, so I was okay. So I was nice, I kind of saved myself a bit here. But yeah, you can get an infinite loop where cat just keeps reading and writing to itself over and over and over and over and over again. So to correctly do this, I need 2 pipes. So I need this in pipe. Yeah?
Sorry, I might have missed the change you made to the child function. Did we rewrite standard in as well? Is that why it keeps reading?
Yeah, so I rerouted standard in and standard out. Yeah.
So what we saw earlier when the program was hanging was not cat reading and writing back and forth. It was because it read nothing from like the right side of the pipe and just like.
Yeah, it read nothing and it kept its own file descriptor open, so it's just hung there forever like before the break. Because I didn't actually do anything to like start it off reading and writing to itself. All right, so to do this properly, I need to close this, so I'm just getting information out of the pipe. And I need another pipe that I can write into. So we need to create another pipe. So we'll call this one inpipefd. Creative naming. So in pipefd, easiest thing to do is think about what needs to happen in the child. So the child, right now I don't clean up anything with inpipefd, but before this executes, I want it to look like this. So I want file descriptor 1 to be the right end of the pipe, which is something I've already done. And then I want file descriptor 0 to be the read end of the pipe, which is the read end of inpipefd, because I'm going to use that to go the other way. So I can just do ye old copy pasta and do efficient programming and just replace out, just replace out with in. So was that super efficient? I mean, it was super efficient. Was that super wrong? What do I need to change to make this right now? Yeah. Yeah, the indices. So I don't use the right end of this pipe in the child, so I should close the right end of the pipe immediately. And here I want the read end to be replaced with file descriptor 0. So this should be the read end of the pipe. Then after that, I close it. So this is the correct way to do that, such that when process 101 executes, it only has these file descriptors open, right? And they point to the right things. So everyone okay with that? Yeah?
Question, what happens if I try to write to the read end or read to the right?
So if we try to read to the right end or write to the read end, we'll get an error. We'll just get an error from the system call saying no permissions or something like that. All right. So in this case, so let's flip it around. So here in the parent, I want to read from the, I want to read from the out pipe and then write to the in pipe, right? The in pipe is what I'm sending to that process. So this should be in pipe FD, and then I should close the in pipe. All right, anything else I need to do? Probably clean up my file descriptors, right? In fact, I think I deleted a call to close, did I? Yeah, I deleted a call to, call to close. So the parent immediately does not use the read end of in pipe, right? So the parent does not use the read end of in pipe and also does not use the right end of out pipe. So I should fix my indices. So immediately, if I'm doing good practices, I should immediately close those two, right? And then here, I write the string testing to in pipe, which in this case will go to standard in to my child, and only to standard in my child, and it will read it. Then I close it because I'm done with it. I should definitely close it when I'm done with it. Otherwise, we might have problems. And then here, I read from the out pipe. So this should be exactly what that child actually sends over its standard output. So I read it. Whoops. I don't need two read calls. There we go. And then I need to close my file descriptor. I have closed too much, so I need to close out pipefd 0. All right, that looked good to everyone. We should be able to communicate with our process we have now created. So if I run this, if I compile and run this now, and I do cat, it should work, right? So, yay. Isn't that cool? Ish. It's as cool as it gets in this course. Sorry. So, first question, if we want to, okay, first question for you. If I forget to close the right end of the pipe here, will my program hang forever, yes or no? Oh, I see head shaking. No? Why? Just because it's not closed doesn't mean it's not written to? Yeah?
If the read end is closed,
So if I don't close it here,
And there's no person who wants to write to it or read to it otherwise.
so my child wants to read from it, right? If it's cat, it wants to read from it.
After that will close.
That will close?
That end, the child is going to close itself after.
The child won't close itself if it's possible that more data comes into the pipe though, right? Yeah.
Yeah, so cat stays open while it's trying to read more stuff.
Yeah, cat stay open while it reads more stuff. Let's make sure. Okay, I'm going to clean up all my orphans and stuff. So pid of cat. How many orphans did I create? Just one. Let's kill orphans. Again, only in this class. All right. So I removed that, and you said that cat will just sit there forever. Turns out this is why debugging lab 2 is going to be hard. So I do this. I read the screen testing. Parent goes. Did I create a forever orphan? Pid of cat. No. Oh no, why? Well, because in this case, the parent just read the testing string, and then that's all it did. It didn't wait for more output or anything like that. It terminated, which also closed the right end of the pipe. So it closed when it terminated, and then in that case, my child's going to terminate because all the right ends are done then. So even if I forgot this one, this will work, although it's really bad practice. All right, so if we're a good parent, what should we do to make sure we're a good parent and a responsible parent? Yeah. Yeah, wait. I need to wait on my child, right? So if I'm a responsible parent, thankfully I know the PID of my child. It's called, so it's just called, in this case, it's called child PID. So I can call wait on it. So I'll just wait, give it, whoops, W status equals, who cares? Check wait, W status, wait. And then after wait, I'll just write a few asserts just to make sure that good things are happening. So I'll do W if exited. I'll just try and make sure that this, assert that it's definitely exited, and then assert that the exit status is equal to 0. Just some asserts because I don't want to bother with it. And this is why it didn't go in an infinite loop before. Excuse me. So yeah, I could also wait PID for it, whatever, it doesn't matter. So now if I run this, properly closing stuff, it's okay, it just prints testing. But now, when I forget to close the right end of the pipe, now when I forget to close the right end of the pipe, now bad things happen. Now it freezes. Why? Well, because I still have the right end of the pipe open, right? And the parent does not terminate until the child terminates. The child is waiting until, remember what cat does. It just constantly reads and reads and reads until read returns 0, indicating end of input. So in this case, if I don't close it, then I still have the right end of the pipe open. And if I'm nice and I wait for my child to terminate, well, the right end of I'm not going to close my right end of the pipe, and it's going to stay open, and my child will never terminate because, well, read is not going to return 0 in my child. So depending on how if I'm a good parent, right, I could ignore that before and get lucky, and my program works. But then as soon as I become a responsible parent, bad things happen. All right, any questions about that? That's fun. Yeah?
So does a parent terminating automatically close the right end of the pipe?
So when a process terminates, it automatically closes all of its file descriptors. And that's why it worked before, because I wasn't actually waiting on anything. Cool, huh? Ish, yeah. Yeah, the whole purpose of dupe2 is so I can modify explicitly what file descriptor 0 points to. Because that's how I'm trying to rearrange it in my child process. Because whenever the child process runs, right? Since it uses the standard file descriptors, it will always just read from standard in and write to standard out. But I can change where it actually goes by changing what those file descriptors actually point to. Yeah?
What if you want to like set file descriptor 2 back to standard error? If you like set it to something else.
So if I want to set file descriptor 2 back to standard error, if I close it, I've lost it. So I can't, unless I know what it was originally, I can't restore it. So if I close it, I close it. And also, another nice benefit of programming defensively here, too, because of the asserts, if I just type a bunch of gibberish, that's definitely not a command, I get a whole bunch of nice error messages here, too, that I can kind of dissect what the hell was going on. So execlp failed, right, in my child, and then it wrote to standard error. So good thing I didn't change standard error, right? If I changed standard error, I wouldn't have been able to see that output. If this output went to standard out, I wouldn't have been able to see it, and debugging would have been a nightmare. So this is why we have a separate file descriptor for standard error that you probably shouldn't touch, so you can actually debug your program and have a hope in hell of doing that. So this went to standard error from the child, and then this is from the parent. So the parent got an assertion, it waited on the child, and the child, well, it terminated with an error code that was not 0, whatever standard, whatever the error it got is from error no, and then, well, my shell told me that, hey, the process I just ran also terminated by a signal sig abort. That was from the assert happening from mine. So, any questions about that? So fun debugging thing too. If you have royally screwed up your file descriptors, and let's say here I create my pipes, and then let's close file descriptor 2. So if I close file descriptor 2, and I do this crap again, what's going to happen? Probably, I'm not going to see a damn thing, right? So if I've screwed up file descriptor 2 and I do this, I don't see anything because my process is still writing to file descriptor 2, right? But I never checked errors from trying to write to file descriptor 2 or anything. File descriptor 2 is invalid, so it tries to write to file descriptor 2. If I straced it, I would see that it got an error. I don't check the errors or anything like that. Yeah?
I guess like what I was asking earlier is, let's say you change file descriptor 1, which was originally standard out,
Yeah.
to in pipe fp 0, let's say.
Yeah.
And then there's no way to like change it back to standard out.
No. No. Yeah. If I make standard out or error point to like replace what it's pointing to by something else, they now point to the same thing and the original thing's lost, unless something else was pointing to it and you saved it and stuff like that. All right, so another thing you'll probably run into in the lab is, hey, let's say before all this, let's just make a very small program. So if I do this, trick question, if I do this and run it, what do I see? Hello, not a trick question. So if I do this and I run it, oh, it needed another argument. OK, that was a trick question. I tricked myself. All right, so now I print hello, right? Now, if you want to really screw with someone that's just learning C, just start your program off and just say, hey, if you put this at the top, it will make your program run faster. So if I do this and try and run my program now, what do I see? Absolutely nothing, right? Did it try and still write to it? Absolutely. But nothing happens. This line's still executed, but I don't see anything because I close file descriptor 1. And of course, we've never, ever, ever checked for errors from printf before, have we? So if we checked for an error from printf, we would have saw that it got an error, but we just ignored it, right? So if you really want to screw with people learning C, you should tell them how to fix it after, but just tell them put close 1 at the beginning of your program, and you will enjoy speedups, which is technically true because it'll just get an error, which is a lot faster than writing data. So just remember, I'm pulling for you. We're all in this together.